All right, so I'm going to be talking about the strengths and the limitations of equivariant networks. There's a lot of work. I mean, in the tutorial, I was talking a fair bit about the strengths, I would say, and I'm sort of interested in not everyone is using an equivariant network for everything. So I think there are clearly places where an equivariant network has a strong advantage. There are places where you probably wouldn't think to use one. And then there's some fuzzy boundary, I think, where maybe people are and shouldn't be, or aren't and should be. And I'm that's sort of what I'm interested in. I'm both interested in studying and understanding it, and also maybe changing our habits there, developing technology that change what you should do. Okay. All right. So equivariance is meant to address some of the big current problems in machine learning. So limited generalizability is a big problem with models. You train on some training data. You usually don't get much beyond what you train on, and overfitting is obviously a big problem. So even interpolation can be an issue. Data hungry models, I mean, in many domains, it's just taken as a given that there be outstanding amounts of data. But in science for AI, or AI for science, and this is a lot of people are interested in here, these are often data poor regimes, right? If you're dealing with experimental data or very high dimensional state spaces, you don't have a Twitter's worth of data to change your model. The other thing is huge models, right? For a university setting. Where we are, this is a big deal that I have a certain number of GPUs, but I don't have meta number of GPUs. And so large models are getting bigger and bigger, and it limits what I can do with them. And the last problem is the black box problem of neural networks, which is they train and they work, but you don't know when they're going to stop working. And so applying them in a mission critical application is not really something we can do. And so we would like to be able to prove things about neural networks and provide guarantees. So these are ongoing problems with machine learning, despite all of the success. And my research program is about how symmetry can not necessarily solve, but address a lot of these problems. If you incorporate a symmetry into a neural network, right, it automatically increases generalization because you generalize across the symmetry group. It deals with limited data because it makes the model much more sample efficient, because whenever you train on a sample, you train on various symmetric transformations of that sample as well, automatically, right? The sort of guarantees and physical consistency is sort of addressed when the symmetry goes into the neural network. It gives us a provable mathematical constraint on the behavior of the neural network, which increases our trust in the model. But it also, right, if we take physical symmetries and build them into the neural network, then we often see dramatically improved physical fidelity, since we're respecting the symmetries of the system, and we often see a consequent improvement in the conservation laws. Okay. And so here's my high-level model for how to do equivariant neural networks for physical dynamics, right? So I identify the first principles model for the system that I'm studying. So what do we know a priori about this system? Then we look at that and we say, what are the symmetries in this first principles model? Then I build a network that is constrained by those symmetries that we've identified. So I throw it, there's information loss here, right? When I'm building the neural network, I don't look back at, say, my system of differential equations. I've actually thrown it away by that point, and I'm just looking at the symmetries. That's partially because of who I am as a representation theorist, but also because I think the symmetries are the right amount of information to not over-constrain the network and build a network that is flexible and can work on partially observed systems, or systems that maybe have related but not exactly known dynamics. Okay, and last, you have to train it, right? Which can also be a hard part. Okay, so here's your one slide primer on group theory and representation theory, but you're physicists, so you already know this. So here's a cyclic group of order 4. So this is the abstract symmetry group. So this is what a group theorist can, this is the data of a group. So it's all a group is to a group theorist, right? It's just the abstract concept of a 4-element set that when you compose the generator R with itself 4 times, you get back to the identity. And that's the complete data. There's nothing else to it, right? But then to make that actually concrete, right, you create a representation of this abstract group. It's like a template, and this is an instantiation on some data. And so we're instantiating it on R2. We're saying what does this abstract form of symmetry look like if we apply it to R2? And since this is a operation, which when I do it 4 times has to give me back the identity, I can map this to a 90-degree rotation. Okay, but the same abstract symmetry group can have different representations. And so a perfectly other good representation of a 4-fold symmetry is to take the cyclic permutations of the standard basis vectors of R4. Right, again, we get a matrix, which when I multiply this matrix by itself 4 times, I get the identity. So if you get bored, go ahead. All right, and so how does symmetry in groups and representations interact with deep learning, right? This is this first principles thing. You stare at your function, the true function that you have that you're trying to model, this f that goes from some rd in to rd out, and you ask what symmetries does it have? And the way a function has symmetries is through equivariance, right? Which means that when I transform the input, I have a clicker so I can walk and gesture. Yeah, okay, great. So like it says, you know, if the way you read this, right, if the input is transformed by some symmetry G, right, then that is equal, and then I apply the function I'm interested in. That's the same thing as if I apply the function and then apply the symmetry. And the row in and row out is just saying that the same symmetry can act on the input and output space in different ways. As we just saw on the last page, the same symmetry can have different representations. And so here's the example. This is image segmentation, right? Here the function f is taking the image of the tiger, and it is replacing the color channels with semantic information about this pixel is part of a tiger, this pixel is part of water, this pixel is part of grass. So it's labeling what it sees in the image instead of its color. That's what segmentation does. And you can see, obviously, this problem is rotationally equivariant, which is to say, if I segment and then rotate, that's the same thing as then rotating and then segmenting. So segmentation is equivariant. And so now you might want to say, okay, I should be using rotationally equivariant networks to do semantic segmentation. And you're right. All right. Okay. And so like mechanically, how do I build a neural network so great, I want to use an equivariant neural network. How do I build an equivariant neural network, right? Okay, so basically, a neural network, right, is a composition of a bunch of functions, a linear function, a nonlinear function, a linear function, nonlinear function, and so on, okay, to like first order. And we have this group G, which is acting on all of these vector spaces. The action on the input and output vector spaces are known. We have to choose which representations, row 1, row 2. How should symmetry, say, rotations, act on these hidden spaces? You choose that. Now the problem is just like a math problem that's 100 years old. It says, what are the equivariant maps, right, that go from RD1 to RD1, or sorry, RD1 to RD2. Like to make this concrete, right, let's take the example of C4. Let's use the 2 representations I showed you before. So we have these 90-degree 2x2 rotation matrices on R2. I'm looking at the M2 there. And does it have lasers? Okay, looking at M2 there, right? So, right, this is like a 4x2 matrix, right? It's got 8 entries in it, and I'm curious, what are the equivariant ones that are going to commute with this 2x2 rotation matrix is the same thing as doing that 4x4 rotation matrix afterwards, right? That intertwining. And so that's just like a math problem. You can write it down. You can write down my little 8 unknown matrices, multiply on the left by 1 matrix, the other one. It gives you a linear system. It has 8 unknowns and 8 equations. You solve it. You find the system has rank 6, and it has, therefore, 2 free variables. You write down the basis, and this is what you get, right? So this is the 2-dimensional space of linear equivariant maps from R2 to R4 under that action. Okay, so if you do this little exercise, right, that's how you build an equivariant neural network. You can if you want, because and so like, right, you can consider any problem, any groups, right? Your life will be harder if you're not doing C4, R2, and R4, right? If you're doing, for example, like SO3 and L2 space, then like you have to work harder to find the linear intertwiners, but it all boils down to this. This is what you're doing. And in fact, you don't even have to do this exercise, because finding the linear equivariant is called an intertwiner, and finding the intertwiners is what representation theorists have been getting paid not very much to do for the last 100 years. So you should crack open a book and you're going to find the answer there. Okay. All right. And there's the little math equation that you can check. All right. And then the nonlinearities also need to be equivariant. So that's important too. All right, okay, and then this is the picture that we get. So we had this big optimization space of all the functions, f theta, right? And neural network optimization means I start randomly in that space somewhere according to some initialization distribution, and then I move by gradient descent towards that true function marked by that black dot, right? And then when we're doing here, and this is kind of like the thing that's like a little bit different from the way like constraints or knowledge is often applied, is we're not applying the knowledge of the symmetry like as an additional loss term or additional data that is driving us towards this symmetric function. We're actually applying the constraint a priori to the model class, right? So that means at initialization, when I have a random function which doesn't do the job at all, it still has the correct symmetries built into it, even though it's doing something random. And the entire optimization problem is taking place within the subspace of equivariant functions, right? So, I mean, to me, you know, if you think about optimization, this I think immediately like raises some questions about equivariant neural networks, which I don't think we've fully answered. So maybe people in the audience can think more about that, right? Which is like when you add constraints to an optimization problem, even if they correctly describe the true minima, right? They may inhibit or hurt the optimization problem, right? They may be over constrained. It changes the optimization problem. You can no longer go where you used to go through the loss landscape, and so you might get a better or worse situation. In practice, and what this talk includes limitations of equivariant neural networks, so I won't talk a lot more about that optimization challenge, but it definitely is there. Okay. So I think I once gave this talk where I just talked about limitations because that's like what I had worked on most recently. But I realized if I skip the beginning part and you're not that familiar with equivariant neural networks, then you might leave thinking they're awful. And so I don't want you to think that. And so I'm going to talk for just a couple minutes about how amazing they are. Because this talk was really like, I think, meant to be a response in some sense to like it's not hype, right? It's just they work a lot, and it's like, you know, but there must be an end, right? There must be a limit to how good they are, and so I want to illuminate that and not just keep always assuming that everything will work well. But I do want that bedrock of they're pretty good. So here are some domains in which our lab has applied equivariant neural networks successfully through collaborations with various domain experts. So on top is fluid mechanics problems. We've done trajectory prediction in pedestrians and autonomous vehicles, various computer vision problem. And on the 5th floor of ISAC here, we have a robot laboratory where we've applied equivariant networks to robot learning. Okay, so I'll talk about 2 of these. So for turbulent flow prediction, so I talked about this at the summer school last week a little bit, right? So here's some scaling law symmetry that the Navier-Stokes equations satisfy, right? That's if you anisotropically scale space and time and velocity by different factors, it preserves the flow with the same constants, okay? And so that's the system symmetry. And here we're not gonna have time to like go deeply, but basically what I'm showing on that first slide, that's the formula for CNN. So if you know deep learning, that formula is fairly familiar to you, maybe modulo using vector notation for pixels, but that's the standard CNN. And why does it work? It works because I'm summing over Z2. That's the group of discrete translations. And that's why it's translation equivariant. And so hopefully, even if you don't have like time to study the equation, you can see by metaphor, right, that this equation down below takes the philosophy of move the same kernel over the input at all translations. And now I'm summing over the group of translations and different scales. So you can imagine I'm moving the kernel around and applying it at different scales. And this way in which I am applying the kernel uses a group action, which is derived from the physical scaling law in the system. So I'm taking the system symmetry, the scaling law, and building it into the neural network operation so that it will be equivariant to that operation. That's a general story called group convolution, and this is a specific instantiation of it for the scale translation group with some discretization, right? And then this is the payoff. So Two things I want to highlight here, and I'll just show you like a number in this table. But what you're looking at here is some sort of magnitudes of current flows in an ocean. Do you have a question? There's a couple questions. Oh, we can ask questions. Yeah.
Sure.
I think there's questions at the end, so we can borrow minutes from there.
It's just a quick question.
Yeah.
In this previous slide, you could do that with any group, like SO3, like you said. It's harder, but you could do this.
You can do this. Yeah. Formally speaking, this group convolution exists for any compact group or any locally compact group with compactly supported signals.
Thank you.
And we're doing both here because yeah.
Just to make sure, I mean, I think I understand, but I want to make sure. The story changed a little bit compared to a couple slides ago, because it just looked like an MLP before, and you were just assuming that your intertwiners were making the affine things nice and equivariant and the nonlinearities. But in this group convolution story, you're splitting the domain of the function sort of into features and base space, so to say. Is that right?
Okay. I'd love to
look different.
Okay. Yes, that is a great astute question. So here's the relationship. You know, this philosophy of like saying, I think I outlined, like I said, like, oh, take a big MLP, apply your constraints, solve, find the subspace that's equivariant. Okay, you can do that in this case. Okay, you can do it carefully, and people do. Actually, there's like a package for it, right? But like, what you will find is this operation. So this is a more mathematically succinct, principled way to parameterize the space of intertwiners. So it's almost like I like gave you a way to do it for any group, but like in practice, actually, you can make an ansatz. Like you can guess what are going to be the intertwiners and actually construct them in other ways, and then you can try to prove you found them all. So that's actually what happens here. Right. So like just in the case of CNN, right, if you take the group Z2 of translations, if you sort of like make things simpler by assuming that there's like a wrapping action on your domain, you can actually exactly solve the problem I laid out. You can apply an MLP to an image input, have these translation actions, and solve for the translation invariant ones. You will get a giant matrix with a big weight sharing scheme in it like I showed. It will turn out to be the expanded Toeplitz matrix that corresponds to doing conv2D. So by recognizing that that Toeplitz matrix is convolution, gives you a more efficient GPU implementation. Does that make sense?
Yeah, it does. And this splitting of I mean, it's just also the domains sort of look different. I almost want to use bundle language and just say that the first picture was like talking about the total space, and here you're sort of the channels in the domain are like the fiber in the base. Is that okay at the metaphor level?
Yeah. So if you have a setting like that, that's the specialization where your group has some sort of semi-direct product structure, or maybe your representation is an induced representation. That gives you a way to solve that constraint problem besides just doing Gaussian elimination, right?
I'm happy with that. Thank you. I understand better. And Sergey had a question too.
But there is like a package out there called EMLP from Mark Finzi where it literally just it doesn't actually do Gaussian elimination there, but you can plug in an arbitrary group and solve the constraints. Yeah.
I wanted to follow up on the first question regarding what kind of groups we can take. So suppose symmetry is trying to become bigger, really huge, go to infinity. So we get something like infinite dimensional group. So on the one hand, one could imagine that that's a good thing because now it's very constrained. But
yeah,
I would wonder, it could also be that it's hard to handle such a big symmetry. For example, has anybody experimented with a monster group or groups of
That's a great question. Not to my knowledge. You know, there's a lot of people, not to my knowledge, but if you have some idea for some application involving the monster group, then that would be super cool to try. I wouldn't imagine that it actually would be like something like that is going to have well-studied intertwiners. So like we can instantiate them. Again, we're not really going to be solving it's not really for us to do Gaussian elimination and solve the constraint problem, right? Like probably what happened is somebody guessed some intertwiners in this space and then proved that that's all of them instead of actually like doing numerical linear algebra. Like so. I mean, standing here and knowing nothing, but being brave like I am, I think it will work. Like a good example of that is maybe like there's the group called deep set, or there's a algebra package called deep sets. And basically what they did is they solved for the intertwiners of the permutation group, right? And if you do the intertwiners for the permutation group on the entries of your matrix, you'll have 2 free parameters for arbitrary sized inputs, right? So it's extremely constrained. You're going from like an n by n matrix with n squared free parameters to 2 free parameters, right? But it still works. 2 is enough. You bump the channel dimension up a lot and you're good to go. So good. Okay, so what lessons? So first of all, this is sea surface. This is ocean flow. I don't know if which ocean this is. Ray, which ocean is this? Can you tell from looking at it? South Pacific, as everyone. Okay, so transport you to the South Pacific, and here's the ocean flow reanalysis data from like satellite captures of ocean temperature, of ocean surface fluctuations, right? And this is the system we're trying to predict these ocean flows, right? First of all, good example, I think, of when deep learning is useful for doing something like solving current flow problems, because that's not a problem you can easily numerically solve. We don't know enough about the initial conditions or external forces or boundary conditions in this system to like easily numerically solve this differential equation. So a really good opportunity for deep learning to show itself. And secondly, so the ESC over there is the energy spectrum of the fluid. So you know, fluids, these things are chaotic, they're turbulent. You can't exactly like just see how far off your velocity vectors are in a long-term rollout. So often what people in fluid mechanics do is they break the fluid flow up through a Fourier transform and look at the amount of energy that exists at various scales in the fluid. And like one of the big ways that you evaluate whether your fluid solver is doing a good job is whether it's capturing those energy scales well. So that's what ESC is. Are we capturing the energy scales well? And you can see for the non-equivariant baseline, right, these test values are like 0.83, 0.75 on the right. And down, if we look at like the rotationally equivariant network, we get 0.43, 0.28. So to me, this tells the story that we're fulfilling the promise that by imposing system symmetries on this problem, we're producing much more physically realistic answers that are doing a better job representing the true energy distribution in the system. So that's the strength of equivariant neural networks. Yes. They're here. So if you look on the side, so there's uniform motions, rotation, scale, and just sort of a magnitude, which is sort of a decoupling of resolution and scale. So we're applying the different system symmetries independently to the networks. The obvious question is, why didn't we do them all together? The answer is that you sort of plateau. So as you add more system symmetries into this deep learning model, what you find is that the errors sort of stop going down at some point. So you can debate about whether that is because like the model has started to become over-constrained, like I suggested might be happening if the symmetry group gets large. So we do them all the symmetries. Okay, so it's 9:30 now. I started at 9:05, 45 minutes, right? Okay, I'm good. All right. Okay, I'll just do some robot learning because it's fun. Okay, so here's a robotics problem. This is so like a lot of what my collaborators work on is grasping, and you're dealing with sort of pick and place problems. So it's not really about like long range sort of reinforcement learning. It's really about like often like just the difficult dynamics of taking a robot gripper and picking up different types of objects, right? So here is a block, this yellow block, and the goal here with the, I think I have a, will it? Okay, yeah. So you can kind of see the robot is pushing the block. So that's that action A. S stands for state in this Markov decision process, right? So it's pushing the block. And so what you can see is there's system symmetry here is that if the block gets rotated, if the whole like world gets rotated and I rotate my state and action, right, then the resulting state that is the result of doing that action on that initial state, which I call S prime, right, is equivariant to this 90-degree rotation. Essentially, because we're just looking at the table from a different angle, really, right? Does anyone want to object? Sometimes people object. But like the robot itself is mounted at one point on this table, and it is not transforming in my system symmetry. So if you actually like include the various like pieces of the robot in your state, then this is no longer symmetric. So we don't do that. So the system state abstractly represented, right, is just this pictured here. It's just the top-down image of the table, right? Okay, now what I'm visualizing here is the Q function. So this is one way to do reinforcement learning, is to train a deep Q network. The job of this neural network is, given the system state, right, it's to tell me where to put the gripper arm in order to pick up that block. Okay, and the way, this is a 4-channel image map that is telling me where I should put the gripper. So spatially, I think it's pretty clear. You see those green dots? They're sort of over the position of where the yellow block is. So that's a good position to put the gripper. But the gripper can also be in different orientations, and that's an important part of the problem. I've simplified the problem to say that the gripper can only be in like these 4 different orientations, right? And you can see the brightest green dot corresponds to this orientation, which if you think about it is the correct orientation for picking up this block, right? Because the gripper arm is actually quite small. It can't get wide enough to pick up the block the other way, okay? And so that's what that Q map is telling me after training it using some sort of TD loss. I find this instruction about the best way to pick up the block. That's what the neural network encodes. And this has the symmetry that I talked about earlier. And this is actually a really fun one because this is a steerable feature with a regular representation, and it's like organic. You often don't see those as sort of organic input features. They're often just used as latent features. But if I rotate that block, you can ask what happens to the optimal action, right? Well, I should rotate all these images because the location where I'm picking up the block has changed. So all of those rotated, but also they permuted, right? Because the orientations have now gotten switched, right? When I rotated the block, the optimal location for orientation for grabbing the block also got rotated, right? And so now this feature map both rotates and moves one over because it corresponds to a different orientation in the gripper. Okay. Okay, this is just saying, right, that if you have this sort of symmetry in your MDP environment and you solve the Markov decision process to find the optimal policy or Q function, then that policy or Q function should actually be invariant with respect to the symmetries, which means that this is a good inductive bias to use if you're doing deep Q learning. Okay, and then we actually deployed this model for actual like on-robot learning, and it can perform a variety of tasks and learn them very quickly doing it. And here's like just this example that we did, right? So this is a separate paper. This is clutter grasping. So here what we do is we fill all these objects in this bin. They're all stacked on top of each other. Finding the optimal like way to approach this with the gripper is a non-trivial problem. And we're generalizing over objects. So actually the model has seen a bunch of objects and learned how to pick them up and is now being asked to pick up completely new objects just based on sort of seeing their point clouds. And this can be trained on an actual robot within an hour, 1.5 hours, right? Whereas the previous sort of best for doing this kind of clutter task for on-robot learning was on the order of 500 hours. So, and that comes from the sample efficiency of imposing the system symmetries. Okay, so that was the first half. So now you think that equivariant neural networks are the bee's knees, okay? And so now here are my questions about like, when do equivariant neural networks stop working? And what should we do, right? So already like when I give the previous stuff, I already start to like bump up against sort of these types of problems, right? So, you know, suppose, you know, I'm looking at like the symmetries of the Navier-Stokes equation. I'm claiming that they're, you know, SO3 equivariant, right? But like, you know, if I look at the fluid dynamics, right, there's gravity. Right? Gravity is breaking the symmetry in the system, or there are boundary conditions. There are boundary conditions that I don't even know about that are breaking the symmetry of the system, right? And so like, if you start thinking about these things and you insist that they, like the symmetry hold exactly, like you will rarely get to actually apply an equivariant neural network, except for the sort of molecular property predictions with point clouds. Those hold pretty exactly. But for like our fluid flow problem, we would just be like, nope, guess it doesn't work. right? Here's some like jet flow that was captured, using, you can see the noise, you can see the gluing, right? Where the different like locations were stacked together. We're training the neural network on this data, like our very observations sort of contain symmetry breaking factors in the dynamics. And the last one, this is like one of the places where this really first came up for us. So this duck that's, I don't know why it's rotating, but this is like a simulated robotics environment. Imagine your goal is to pick up that duck. So remember how I said we need like the arm not to be like in the frame breaking the symmetry of the problem. We have this idealized top-down view of our model field so that a 90-degree rotation actually like gives us the system symmetry, right? Well, when we're doing real robot learning, do you think we ever like perfectly get a camera with a perfectly like isometric viewpoint without any like background or anything like? No, we never get that, right? In fact, the biggest problem we have is most of the time you can't really get the camera straight down because the robot is getting in the way. And it's like not safe. It's like we always mount the camera slightly off to the side, right? So now if you think about a 90-degree rotation of the image, it's different than a 90-degree rotation of the like system state, right? So I think what you're seeing here is this is the system state rotating, which is different than me rotating the image, which would be the same if it was a perfect top-down view, right? Okay, so these are all like problems. So here's my little like toy. So one like thing that I am sort of trying to understand better these days is the various ways that the symmetry might be approximate or not hold exactly. And I think that there are sort of a variety of ways, and we haven't like settled on all of the exact correct definitions here. And I think which problem you have determines what you should do about it. So here's a picture that's just like a very simple idealized picture to explain the various types of approximate symmetry that you might have. So this is a classification problem. I'm just showing you points in R2. The input space is just points in R2, X, Y, and then the output of the neural network is to classify this point as being blue or green. Okay, so you notice like I put the points that are in the center close to the y-axis to be green and the points outside further to be blue, right? And like with many machine learning problems, the input distribution does not cover the input space. I mean, it can't, it's usually compact, right? And so the points that I actually am trying to classify are sort of clustered in a narrow bar around the x-axis. So does that make sense? And this problem has C2 symmetry. So notice if I reflect over the y-axis, right, the labels are the same. And so if I imposed C2 invariance in this problem, essentially ignoring the sign, that would actually probably help me learn this problem since the input space would be cut in half, okay? All right, so that's correct. I call that correct. That's correct symmetry. That's the case where you want to apply an equivariant neural network. Okay, but here are several ways that things can go wrong. And I claim that in many realistic cases, these are happening to some slight degree. Okay, so one is that you can have some sort of like shift here, right? Suppose like these points are not exactly over that axis, right? So you can imagine some of these blue points, right, like are actually getting, if I reflect them, over onto green points. And so if I impose C2 symmetry, that invariance would force me to say green or blue on two different points that actually have two different colors. So it's not actually invariant over the entire domain, right? It is largely, it's a very small shift, and the inductive bias is mostly correct, but not entirely, right? Here I have, I don't know if it's coming across, I made it a little bluer, you see? So it's like, instead of 0, it's like 0.1. Okay, so this is sort of epsilon approximate equivariance. When people write down what they mean when they say approximate equivariance, I think I had and others have a tendency to write this down, right? But it's just one way that things can go wrong, right? So that's convenient. It's just the answer of the function is not exactly what you expect it to be. It's a slightly different shade of blue. And then this is what I often see. We call this extrinsic symmetry because in this case, or we say rather, the C2 symmetry group has extrinsic symmetry relative to this function, right? Which is just saying that you can see what has gone wrong, right? Which is that the input distribution under a C2 reflection is not mapped exactly onto itself, right? That symmetry is mapping you a little bit out of domain, but it's tantalizingly close to being a correct symmetry of the system. And your brains are probably already thinking about ways to solve that problem, right? Okay, and so my contention is that there are different ways to solve these problems. And so I have 10 minutes, and so I will talk about one of those ways. Okay. All right. So here's a paper in which we talk about applying equivariant models in cases of extrinsic symmetry. Okay. All right. So formally speaking, here are what I contend are the sort of assumptions under which equivariant neural networks are usually applied. So first, there was the equivariance equation, which you saw already, and I emphasized. But there's this second assumption, which people sometimes quibble a little bit, but I would say broadly speaking, this is an assumption that you have in mind when you apply an equivariant network, which is that the input distribution is preserved by the symmetry. These are transformations that take input samples to other input samples. Otherwise, sort of why are you considering them? Okay, and so let me show this sort of 3 different kinds of symmetry that we classify that sort of correspond to what I showed you before. So this is a classification problem, but I've stretched it out into a circle. So classify the points along the circle as either being blue or orange. Okay, so if this has correct symmetry with respect to flip. So if I flip, I'm mapping blue to blue and orange to orange, so that would be correct symmetry. Okay, if I'm doing rotation by pi, this is straight up incorrect symmetry. So that considers those cases where I shifted it or it was epsilon approximate, right? So those kinds of approximations. So the network under this symmetry would be forced to make errors, right? And then this is extrinsic, right? So now I'm using the scaling group, and this simply moves points in the input distribution to points that are out of distribution. So those are the 3 kinds that I'm considering, right? And here's our motivating example with the duck, right? Showing you that the image rotation is distinct from the state translation, right? And if obviously it's very, like image rotation, I can write a Python function for, and that means that I can see how a matrix is transformed, and that means I can figure out the entry parameters and build an equivariant neural network. But notice that this rotation, like, this is image is input still, but the state is like latent. It's transforming in some way. It wouldn't be easy for you to write a Python function that like rotates the world from a side view. That's like the novel view synthesis problem. Like it's not a trivial problem. And so we don't know how to easily build an equivariant neural network directly to that second kind of transformation. This is just showing like other sort of like symmetry breaking factors that we might actually like encounter in the real world, right? That are observational corruptions that aren't part of the actual state that displays the symmetry, but are nonetheless in our input distribution, right? And they would make the symmetry extrinsic, right? If I rotate the world and there is a shadow coming from a certain area, the state has transformed, but because the shadow moved, I'm now seeing out of distribution data. That was never an observation that I could have seen from where I'd mounted the camera. Okay. And so in sort of this work, the sort of idea of how to address this kind of extrinsic symmetry, right, is largely the idea that you can actually still apply equivariant neural networks in an extrinsic case because the network is not being forced to give you wrong answers. However, it could be beneficial or it might make it harder. It all depends on what the exact relationship is of the symmetry in terms of the problem, like how approximate that symmetry group is. If it's like close and approximate, like that little bent line, it's probably still going to help you. But at some point, the approximation of the symmetry becomes too extrinsic, and you would no longer even call it approximate, right? So here's some picture that might show you why the scale equivariance in this problem can help you, right? Which is if you have sort of sparse input data, and in some sense, like if the data manifold being lower dimensional suggests that it's kind of always sparse, then applying a symmetry group helps sort of flush out the space and adds more points to your problem and can make the decision boundary easier to find. So applying a scale equivariant model to this problem can actually help you, even though you wouldn't say that scaling is a correct symmetry of the system. Okay, so here is an actual example using this side view thing where we apply this in robot learning in a simulator. So we use side views, we apply equivariance to image rotations that are extrinsic because they're rotating the blocks, but they're also like rotating everything else in the scene, including the shadows and the robot and like sort of that slight skew to your viewpoint. And what you see is this symmetry is still close. It's still approximate enough. We're the blue line, right? So And in these plots, what you're seeing is how fast it learns. It's the success rate over time. And in RL, you want to learn faster. So the fact that you have like all of these different state-of-the-art baselines like RAD and DRQ and FIRM, all clustered together, like fighting, you get out your like magnifying glass to find the difference. And then there's the equivariant model, even though the symmetry is approximate, right? Like with a huge gap in performance. So this is useful. Okay, and then here's my favorite. But this is the cautionary tale. So extrinsic symmetry can also be harmful. And it depends on, you have to ask yourself, when I apply a symmetry constraint to a problem, I'm actually changing the problem. I'm solving the problem like in the quotient space on the orbits, really. Let's just think about invariance, right? And you can ask, is that learning problem harder or easier than the one I started with, right? So here's an example of a problem where you can relatively easily see that I have made, even though the symmetry is extrinsic, it's not incorrect, it's not forcing you to make any errors, but I made the learning problem harder. Okay, so we call this the separated Swiss roll. So this is data actually in R3. Okay, and your goal is to classify points as blue or orange. So if you're a non-constrained neural network, there's a decision boundary. You just have to put this plane slice between, and if you're above it, you're blue, and if you're below it, you're orange. Easy peasy, right? Now, what if I apply the extrinsic C2 symmetry, which reflects reflects through the plane at z equals 1/2, right? So if I do that, I'm now studying the quotient manifold. And what that means is I can effectively just reflect those data points down. And this is really the problem I'm now solving, right? So the problem is extrinsic because none of the data points that are in distribution got mapped to any data point that was out of distribution. The spirals sort of don't overlap. They're askew. This is the projection looking straight down, right? So applying the symmetry gives me this learning problem, and this is the Swiss roll learning problem. And you can still separate the blue points from the orange points, right? But it's very hard, right? You have to like create this very nonlinear like separation boundary. So applying C2 symmetry is bad for this problem. Okay, wrap it up. Okay, all right. Okay, I think I just want to show, okay, I think I'll like show 2 more slides. So I was thinking about these birds that like I think was also like part of the motivation for this problem. So like this is like an extrinsic case, and it's asking, when does symmetry hurt the problem? Here, right, there's a data set. You try to classify the birds, okay? Bird classification, that should be rotationally invariant problem. A nuthatch is a nuthatch, a woodpecker is a woodpecker, okay? But here's the thing, like if you look in like Audubon's like identify the birds guidebook, one of the bullet points for helping you tell a nuthatch apart from other birds is that it has special claws that allow it to walk down a tree. And so if you see it like pointed down the tree, oh, that's probably a nuthatch. And so by applying the invariance, the problem is still solvable, right? But you've removed your ability to determine orientation, which was a useful signal for solving the problem, and you made it harder by applying the symmetry. Okay, I think this is the last slide, and then I'll end. Okay, so on this slide, what you see is basically like, as suggested by my example earlier, you can have various degrees. You can combine all of these things in your domain. So you can have correct, incorrect, and extrinsic symmetry to various points in your domain, right? And what you see is this crossover point, right? So here we're applying an invariant model and an unconstrained model, and we're saying who does better, right? And what we see is this is going from harmful extrinsic symmetry. So on the far left, the MLP outperforms because the invariant neural network is getting hurt by the symmetry. And as we alter the amount of symmetry in the problem to make it more correct and less extrinsic, there's a crossover point, at which point the invariant model is benefiting from the symmetry, right? So this is very hard to measure, but in principle, this is what you should be thinking of when you think is, how much of these various kinds of symmetry do I have in my problem? And where am I with respect to that crossover point? And that determines whether you want to apply an invariant model or not. Okay, so that's my talk. I'll just show the thank you slide with the collaborators.
Thank you for a great talk. I'm surprised that you managed to get through a whole talk on symmetries without saying the word augmentations once. It was on your slides, or at least abbreviated on your slides at some point. Could you comment on the, let's say, I mean, alternative isn't the right word, but you know, the other approach to doing this, where you augment your training data set and you just simply show, which would address maybe some of the issues you're raising in a practical way, but I'm sure there are advantages and disadvantages that that you can enlighten us about.
Yeah, that's a great point. Yeah, augmentations. So in data augmentation is another way to have the network learn symmetries as opposed to have them hard coded. So basically, you would, instead of like imposing rotational equivariance, I would just show different rotated samples to the network to make sure it can still identify. So we usually see pretty good at performance improvement relative to data augmentation in like strict symmetry cases because it doesn't use up model capacity. Like really when you're doing that, the neural network never learns the symmetry. It just literally like learns, okay, that is 3. That's the number 3. That's the number 3. What's that thing? Oh, it's 3. 3. Like, so if they're just separate, like sort of like data paths sort of within the network, right? So we usually, for the same number of parameters, the equivariant neural network is going to do better. It just has the constraints built in. But you're right, data augmentations can be used for things that are not strict group symmetries, like noising or cropping, right? And those might help you in these approximate symmetries, where in the a lot of data augmentations are essentially sort of extrinsic. They take you out of distribution. So.
So thanks for the talk, and I need to think more about extrinsic and how it might apply to the data sets that I think about and whether that ever happens. But one thing that definitely happens are cases where you have approximate symmetries. And you had at the bottom of your slide some suggestions of what happens either when you have like small modifications, that is the group actually is there, just kind of moved over, or you have like this kind of epsilon variation. Can you unpack a little bit about the things that are on the bottom of that slide?
Yeah, definitely. What I'll just do is I'll just flash another slide. I'll flash this slide. So this is work with Ray and Rose, and I talked about it more during the summer school, so I decided not to talk about it as much today. But this is sort of what you do in the epsilon approximate case. So literally what we do is we take these sort of intertwiners, which are, so here visualized, so a non-equivariant kernel. The equivariant kernel in this case, as you can see, is the rotationally symmetric. What we do is we relax the mathematical constraints inside the neural network to say that we get an approximately equivariant kernel. So this kind of network is adapted to produce epsilon approximate outputs in this case. Yeah, so here's the paper if you want to look.
All right, since we're a bit over time, I think we can punt the rest of the questions to the coffee break. Let's thank Robin again.